Hello, good morning, and welcome to this Smart Tenants Underpin Deep Dive for Smart Underpin or SmartPin has been known for many different names. This is the second deep dive done in collaboration between Smart Tenants and Underpin projects, and it is focused on semantic data interoperability for data discovery and analytics in the Underpin data space. So, first of all, let me introduce myself. I'm Katia Lavin, part of the Novalia Association team in the coordination of dissemination and communication of the Smart Tenants project. And we're here today to continue in this collaboration with the Underpin project. So, I'm going to very briefly introduce the event and the speakers. As you know, this deep dive is led by Graphwise.ai by Petar Ivanov and Vladimir Alexiev, who are here today, and I will very briefly introduce them right after the event agenda. So we will be starting with with this welcome and introduction session. Then we will have the presentation on semantic metadata interoperability for data discovery analytics in Underpin Data Space, and a brief space for open discussion and questions and answers. So in 2023, two projects were funded under the Digital 2022 Cloud AI Data Spaces for Manufacturing Deployment call. And as part of both projects' strategy for knowledge transfer and open collaborative innovation, both projects, Smart Tenants and Underpin, have agreed to involve in some frequent Smart Tenants Underpin Deep Dive online events so as to expand the European and international knowledge on manufacturing deployments or manufacturing related data spaces technologies, components, and deployments. So with this, I'm going to start introducing the first speaker, who is Peter Ivanov. Peter Ivanov has a bachelor's in science in computer science and management science from University of Edinburgh. He also has a master's in machine learning from the University College of London and in neural systems and computation from the Institute of Neuroinformatics at UZH and ETH Zurich. Peter first joined Ontotext, now Graphwise, in 2016 and returned to the company in 2022. He is currently part of the company's innovation and data teams, working as an AI engineer, and is involved in projects in disinformation industry and manufacturing, as well as healthcare. So our second speaker is Vladimir Alexiev. I hope I pronounced the name properly. He has 35 years of IT experience, 20 years as an IT project manager, and 15 years of semantic integration experience. And in the last 7 years has been focusing on industrial data, including railroads, OTLs, asset management, AECO, transport, logistics data spaces, AAS, DPP, and so many other technologies related to industrial data. He's chief data architect at Graphwise.ai, the result of the merger of Ontotext and the Semantic Web Company, which is the largest semantic technology company in the world. Graphwise.ai has tools for structured and unstructured data management and knowledge graph building, and for integration scenarios of Gen AI and large language models, as well as KG or neurosymbolic computing. As part of this strategy, Graphwise.ai helps major enterprises and government agencies to fulfill their motto, which is AI thrives on whole data. So with this very brief introduction, thank you so much, and I leave the ground to Vladimir and Petar. So please activate your microphones again. Sorry.
Thank you, Katia. So I will start. I will present to you the outline of the today's presentation and also give you a brief description of the project. And I'll then hand over to Vladimir to give you the details about the semantization of the data space and how we achieve semantic data interoperability. So, Vlad, if we can move to the next slide.
Vladimir, are you going to share the screen again, or do you prefer to do it through the Vimeo? You're muted, Vladimir, just so that you know. Now, I think you can speak.
Yeah, I'll share it in a second.
Okay, no problem. Just to make sure. That works. Thank you.
Okay, here's the outline.
Yes, thanks. We'll touch upon four main topics. First is semantic interoperability in data spaces and how this can be achieved via various ontologies relevant to the data catalog and also to the rights who has access to what data assets. We'll then discuss the metadata problems that exist currently in most data spaces. And then how we address those via the UNDERPIN semantic model. And finally, we'll also touch upon the purpose of having semantic metadata and how it actually helps the participants of the data space. This whole thing, just to mention, is done in the UNDERPIN data space. So let me start by giving you a brief description of the project. It is funded by Digital Europe Manufacturing Data Spaces. It revolves around critical energy resources. In particular, we have two main data providers. One is oil refinery, and the other one is a wind farm. Both, I think, are the largest producers in their fields within Greece, and also one of the largest in Europe. The data that we are working with is two types. One is the sensor maintenance data that those data providers share. And in return, they receive predictive analytics data from different service providers that analyze this data and try to predict when a particular component would break. We add a lot of services to a standard data space within the UNDERPIN data space. One is that we go way beyond the standard DCAT model used to describe assets. We also add central file storage and time series database, which eases the onboarding of new participants, so they don't have to set up file endpoints and be able to more easily share data. We also add a vocabulary hub that is set up via pool party, and also we use GraphDB to store the metadata. This allows us to more richly describe the different assets in the data. And we add a lot of other technologies that make all of these things come together, such as the data vault, where a user shares the assets and describes them, semantic search, where users can discover in better ways the different assets that are available. We have GraphDB and Influx that interoperate in order to describe the assets and also to store the time series data. And there's also a visualization dashboard where a user can easily analyze the results of the predictive maintenance services. The metadata that we offer in the data space allows the participants richer ways to discover the different assets. This is achieved via the semantic faceted search. It also facilitates direct ingestion of data into Influx and combining multiple CSV files which store consecutive data, for example, from the sensors into one unified time series. This eases up the analysis process. And we also offer flexibility in how the predictive analytics is achieved, as these services can gain a richer description of the different columns within the CSVs or the influx measurements and figure out what data is relevant to the particular analysis. So then on the next slide, I will briefly touch upon how all the data is shared across the data space. We start at point 1A, which is the data vault. There a user uploads their files and describes them using either pre-existing or created schemas related to the particular system, not only on the level of the whole file, but also specific columns, and within the specific columns, things such as what is the component that is related to the sensory measurement, what does this sensor measure in terms of what units and so on. This data can either be provided simply as a CSV, which is stored in min.io, or in point 1b, it can also be directly fed up to InfluxDB and then shared via the participants connector. This is in point 2. This is where every participant can link the asset that they're creating via the connector to an existing data set that they have created through the data vault. The information about the assets of a particular participant are connected by the broker, which is the service. This is at point 3. It collects all the different assets of all the participants and make them available for search. And this search is richer than in standard data spaces because we have a much more detailed description of the assets, which is stored in GraphDB. And then finally, we have Elasticsearch, which enables us to make all of this metadata available and filterable by other participants who want to discover what assets are available. So on the next slide, we'll see that we have a very large list of standard software that we are using. First, we have the standard data space components such as the authority portal, the connectors, key cloak for authentication, and also HashiCorp, which is the vault used to share credentials among the developers of this data space. We also add storage such as Influx for time series and min.io for regular file storage. We have GraphDB, onto text refine, and pool party, which all enable the richer metadata description. This is then facilitated via Elasticsearch for the purposes of discovering the assets. And finally, we have services such as Chronograph and Kibana for visualization of the data, and Argo CD for managing all of these services. In addition to this, we have also developed a lot of custom software. One of these is ingesting the metadata collected by the broker in GraphDB. We have the data vault that I mentioned earlier that allows the interaction of the user with the min.io and also the description of the assets. We also have direct ingestion of data from the data vault to Influx. We have an editor to create the schemas. This is also integrated within the data vault. We have the semantic search enabled through Elasticsearch. We have the semantic model, the visualization dashboard. We also have blockchain with smart contracts that record all the assets negotiation and transfer so that it can be used for reference later. And of course, we have the two analytics services, one for the refinery and one for the wind farm data. So with this brief description, I'll pass it over to Vlado to describe to you the semantics in the data space.
Okay, so Peter described the software and architecture used in UNDERPIN. I'll describe the semantic metadata that we handle. And I'll start on the topic of semantic interoperability in data spaces. This has been quite a hot topic in the last at least 3 or 4 years. There has been actually two series of workshops, one called Semantic Interoperability in Data Spaces, the other one Semantics in Data Spaces. The first one was organized by the Semantic Web Company, now Graphwise, and the W3C, IDSA, and BDVA. The second one is in conjunction with the WWW conference, or in the last years, it's related to the ESWC, European Semantic Web Conference. There was a workshop by IoT, which is the Association of IoT, Internet of Things, and a few others. It also was a hot topic at the main European data sharing event, the European Big Data Value Forum, as you see here. Now, why is interoperability important? Because it eases consumption of data from a data space. So the data space architecture eases the access to data, but then what do consumers do with it, right? If every data set has its own schema and the schema is not adequately described, then the consumer needs to go and drill down and figure out what it is and implement integration between the different data sets. So even though interoperability is very important, it's also elusive. On the next slide, you see a number of papers, and 2-3 years ago, we talked about that the business data in data spaces should be semantic. But more recently, we now also see that there's a lot of defects in the semantic rendition of the metadata. So that is what we set out to tackle in UNDERPIN. So we've had a number of contributions in some of these workshops, and I'll post a link in the chat to this presentation, so then you can go and explore some of these presentations that interest you. I guess some of the most relevant to this presentation are this one, semantic problems in data spaces, and maybe this one, how we use the LLMs to generate column descriptions for UNDERPIN. This one is also quite important for future work. It's a starting collaboration with TNO, with their semantic treehouse, which is used as a vocabulary hub. And basically, we'll try to productize the experiences we have had with UNDERPIN using GraphVB and Pool Party for other projects as well. The DCAT and ODRL ontologies are fundamental to data spaces. They are the basis of the IDSA data space protocol. And DCAT, at least, also is the fundament of data sharing in Europe in all other contexts. So it is the foundation of the European data portal. There are profiles for statistics, for geospatial data, for healthcare and life sciences, and also national profiles. So within Digit, there is a whole unit called SEMIC that work on this and also on the Interoperable Europe Directive, which just underscores how important semantics is for Europe. ODRL is a language to express rights and contracts and conditions over the use of datasets. Now, the most important implementation of a data space is called the Eclipse Dataspace Components. And in the IoT paper on semantic problems in data spaces, we describe in a lot of detail problems with the semantic rendition that comes out of EDC. I think the root cause for these problems is that EDC doesn't use semantic technologies in its implementation. It puts the metadata in a relational database in Postgres, but this means that it is a lot less flexible than possible, and it is hard to accommodate new sorts of metadata, and bugs take a long time to fix because various namespaces and URLs, they are encoded many times in the Java source code of the program rather than using some object to RDF mapping framework to make that external to the software code. On terms of extension, you see here some detail. For example, it doesn't support the class dataset series, even though it has been in DCAT for over 4 or 5 years now. It doesn't support relations between datasets. There is a way to attach additional metadata, and this will be quite one of the important points of this point, that we use CSVW to describe datasets at the level of columns. But the only thing is that it says, well, you can use the property DCT conforms to link out to something, but there's no standardization with that, what that description should be. In UNDERPIN, in particular, we needed, and we use CSVW for describing columns, SOSA for describing features of interest, QDT for units and quantities. We also accommodate temporal slices of datasets, so a series of CSVs can result into the same dataset series in influx, right? If you know that they conform to the same schema and that they are part of the same series. Some of the concrete problems, wrong namespaces have been used. The JSON metadata payload lacks base and it doesn't use proper URLs for some of the nodes, which results in a disconnected RDF graph. The JSON UD context is deficient, so some properties that should have been defined as object properties are not. There is now a test conformance kit in development, but it doesn't leverage the W3C experience with using semantics to describe tests and test results using these ontologies, and also to use Shako validation or some other semantic validation technologies. And up to this point, the lack of conformance test kit is cited as an excuse. So when we point out some defects in the semantic metadata, we were told, well, no implementation can really conform to the DSP because there is no test conformance kit. But the DSP sits on particular ontologies and Chaco schemas that must be upheld, right? And finally, and which I find most strange, is that some of the core developers of the EDC, they view semantic interoperability as a hindrance rather than an essential component. So they view semantic technologies as overly complex, but we hope to change that view and to show that it is not that complex. Here you see in red the things that are wrong in the semantic description of a data set. So, for example, this here access service, well, it should be a URL, but as you see, it is rendered as a string. A wrong decat namespace was used. So it's a mixture. Some of them are wrong namespaces, others are correct data spaces. There's many things. It's not easy to describe all of them, but it is in our IoT presentation. And what came as a bit of a shock to me is that it became obvious that nobody has converted the metadata coming out of data space to RDF to see how it looks as a graph. So what we did was we designed our own metadata schema that extends DCAT, and then we captured it in GraphDB using some workarounds, let's put it this way. So the UNDERPIN semantic model, you see the table of contents over here. It reuses a number of ontologies for various things. And we also collected several vocabularies for features of interest, for statistical qualifiers, and finally for quantities and units, we just use the subset of the QDT, which is a very popular and also quite big ontology for units and quantities. The semantic model is an open repository on GitHub, and in total the project uses 21 repositories, and we're currently considering and debating which of them to open up. I'll present the UNDERPIN semantic model in 3 slides. So first comes data sets, and there's also the distribution of a data set, which outlines the exact format, for example, text CSV or application influx. Over here we have some particular use of existing fields in DCAT. For example, we have 2 sorts of type. One is it input to resulting data set, and 2 is it a CSV or is it influx? We outline the temporal coverage of a data space using this DCAT construction with these 2 properties for start and end date of a time interval. And this one is fairly important. It links out to the next level of description, namely a CSVW schema. I'll show that later on. I don't show here the ODRL, rights and contracts, because that is handled by the data space. But even though this model is not very complex, not all of it is supported by data spaces. So we capture the the metadata and we put it in GraphDB as semantic metadata. On this slide, I present the relations between datasets that we have. So this here is an input dataset in CSV, and then after it and its siblings are ingested in Influx, it becomes part of this dataset series in Influx. So you see how the types here vary. It's still an input dataset. It sends your data from the machines, but it's now Influx, not CSV. And then when predictive analytics algorithms are run, we keep a link. This comes from the Prov ontology, which relates the resulting dataset to the respective source dataset. So this one was made on the analysis of a single CSV, whereas that one was made by analysis of a complete influx time series. This here is the lower level of description. So DCAT, even though it's very, very important, is just the tip of the iceberg. But to know in more detail what is in a data space, what is in a data set, in our case, because all the data sets are tabular, so we use the W3C CSV on the web ontology to describe them. So you have a tabular schema that consists of a number of columns. This here, this T identifier, is the sequential number of the column. There is a name, title, and comment for every column. Then we have XSD and influx data types. And also if it is a date, then this subsidiary node is used, which describes the format of that date. We also have a flag whether to suppress that column, in other words, not ingest it to influx, because in some of the data sets, there's over 150 columns, but only about 50 of them are needed for the analysis. And then it also refers to features of interest, either general like ambient air or bearing, or specific ones, which are machine tags, for example, refinery compressor 1, 2, 3, 4. There's also qualifiers, things like average, minimum, maximum, and so on. There is also units of measure and quantity kinds, which refer to QDT. So it's these here properties, these two properties. And finally, we have some thresholds. And if a prediction shows that the reading goes outside of these bounds, then it generates an event, so a slightly different type of schema, that an alarm or a trip was raised. Now, this is an example of the columns, some of the columns that we had to deal with. Here on the left, you see the row column name, and you can see two defects right away. One is that the column carries the dataset specific identifier, and this means wind turbine generator 01. But this makes the column definition not applicable to another wind turbine, right? So we remove this prefix. We also remove the sequential suffix at the end, because the same columns may be used in a slightly different order in another schema. So the sequential number we put as an explicit separate field, okay, the DST identifier. You also have some averages here, and even though all of the averages, all of the abbreviations here are understandable, RPM is revolutions per minute, but in many other cases they are hard to decipher abbreviations.
Hello, Vladimir. Just so that you know, you're no longer sharing your screen. I don't know if maybe you changed the screen, but we no longer can see it.
Okay, sorry. Okay.
Now, yes.
So what we do is we decipher the column names into something more readable. In this case, this is just the sensor identifier. And from a separate metadata sheet, we have the column descriptions, but we put them in the CSV ontology, everything in one place. Here's an example of the features, the qualifiers, and of course we turn this to semantic URLs. So we harvest two small taxonomies for features and qualifiers and convert them into semantic resources using SCOS. This here is the quantity kind and the unit of measure, which we borrow from QDT. So I already described these problems. I won't repeat it again. I'll just say that it's quite a lot of work to explicate some of these bigger data sets with like 150 columns. So we used LLMs to automate the process. Here is an example of this. So if you face this column, D bearing temp AVG, okay, so it's about bearings and it's about temperature and average temperature. But what is D? I don't know. But ChatGPT was quite confident. It said this is the drive end. So it's a bearing on the drive end of a shaft. And then we asked it with a simple prompt to generate something like this. And it comes up with quite a lot of information. If you read it, you see it's very descriptive. It captures the features of interest. It captures the quantity kind and the unit and also the qualifier. So it was quite a lot of help to gather the descriptions of these columns. We used some tools in the capture and handling of that metadata. Initially, we captured the metadata in a table and we used OnText Refine to artificize it. But now we have a metadata editor. So when a new dataset comes in, we attach it to an existing schema using an interactive editor and we handle it this way. Okay, in the last part of the presentation, I'll describe what the metadata is good for. So by describing the meaning of datasets and their columns, this enables, first of all, very powerful semantic search. You see it on the next slide. It also enables automated influx ingestion by generating so-called influx table annotations or CSV annotations. And it also enables the more flexible development of analytics applications that can discover columns of interest rather than relying on hard-coded stuff. So this slide is about the semantic search in UNDERPIN. Here on the left, you see the index definition, or some part of it anyway. We use the GraphDB to Elasticsearch connector. In other words, by using the semantic metadata in GraphDB, this definition copies and keeps in sync the required parts of the metadata into Elastic. So some of these fields come out as facets, as here on the left. Others are used for full text search. It's not shown here, but it's also available, right? And we also have auto-completion for some of the fields. So this is the view of one data set. And as you see here, the column characteristics are separated. So we're saying that in this data set, there is columns that describe bearings and axial displacement and compressed air and so on and so forth. And the units in these columns are, some of them are electrical, others are temperature, and so on and so forth. And by clicking on the various values, this restricts the number of data sets to only the values that you have selected. The second application is for ingesting time series data to Influx. And first of all, why did we decide to use Influx? Because for large data sets, it gives a lot better opportunities for analytics. If the data gets very big and it's split up into a number of CSVs, but imagine that there are some important things happening right on the border between two CSVs, right? So by using time series queries, it is easier to get an overview of all of the data and use exactly the time slice that you require. We've implemented an automatic ingestion procedure. So first of all, we derive influx CSV annotations from the metadata. And then when the user adds a new CSV that has the same shape as a previous CSV and will be part of a time series, we skip the columns that are declared to be suppressed. Then we check that all the remaining columns conform to the same schema. We ingest all of these CSVs in the same bucket and measurement. So we use one bucket per dataset. We also establish relations from the datasets describing the CSVs down to the influx time series. And we also generate the metadata for the influx dataset from the metadata of the CSVs, right? And we extend the temporal interval to what is actually in the data. Finally, we create an influx access token that is used by the data space to grant access to a consumer that has signed a contract for that time series dataset. And last slide, it also enables more flexible or generic analytics applications. So typically, you'd write a Python program that has hard-coded column names, but this means that the extensibility and the general applicability of that application is limited. Also, very often the whole data is loaded in memory, but it can only work with so much data, right? For bigger data sets, you need a real time series database. And last but not least, you may generate a result that doesn't have a defined schema. So it is harder to consume, right? So what we do is we ingest those resulting datasets back into the data space to enable better access to them. And we have some simple services to find columns by characteristics. For example, tell me all the columns that are about bedding temperature. These two characteristics together in one column. And finally, we use the same principles in the visualization dashboard that we have. So it is fairly easy to select a resulting data set and the input data set that it comes from, and then to select source columns and predicted columns and see them somehow together to be able to have better confidence that the predictions match the history of the data. Okay, so that was the presentation. Now let's take to some questions.
Yes, thank you so much. It was quite interesting. There have already been a couple of questions, actually. I will leave 1 minute for latecomers to put some questions in the chat, and then we will start trying to answer some of them. I recommend Peter and Vladimir, you can see the chat and give it an eye to see a little bit the questions that have already been posed, so you can prepare. Sorry, now I'm back. So, very quickly, let's start with the first question from Claudia. So, what would you say that are the biggest challenges in semantic standardization in data spaces? Feel free to try to answer, any of you.
Yeah, Peter, do you want to try?
I'll pass it over to you.
Okay, so as part of that workshop on using LLMs for semantic interop, the organizers had They asked each of us to prepare some questions, and my two questions were: in your practical experience, are you happy with the level of semantic description in data spaces, and are you happy with the searches that are provided? And people in general said they're not happy. And I think what is needed is for the commission to make it more mandatory, not just okay, there is a data space protocol, there is semantics, but people should find it between themselves how much to conform to that. And I think that's important because Europe has invested a lot in data spaces. And if everybody believes that interoperability is important for consumption, then more emphasis should be put on that. For example, in the Simple project, which is this huge current project to develop a federation infrastructure for cloud and for data, I'm not aware of a lot of semantic work happening, but I think we'll get there. On the second question, we don't train the LLM, we just used ChatGPT with some simple prompts to generate that data. Then a question from Marcel: to what extent does the significant formal load befall upon a data space end user? Petr, do you want to try that, or should I try?
Yes. A lot of the components that we've added are with the purpose of reducing this load as much as possible. So when the user goes through the data vault to share their asset, the information about the individual columns and what they're describing is automatically extracted. And rather than having to manually enter the information about 150 columns, they only have to go through and validate what has been automatically extracted, correct if there any anything that is wrong. They can also, once a data schema exists to describe a particular asset, they can choose to reuse it. So when they're uploading a specific asset, they can select this conforms to a schema that already exists. Of course, if they don't use the data vault and they have their own endpoint through which they're providing the data, then they would need to generate the additional metadata themselves. But going through the data vault, all of this is handled for them.
Okay, next question again is from Marcelo. Would Datespace users strictly need Graphwise.ai for deploying this advanced level of semantics? Well, definitely no. First of all, we don't have any sort of a commercial offering for data spaces yet. We're talking to some organizations, most importantly to TNO, regarding their semantic treehouse. But there's many semantic toolkits and softwares that can do aspects of what we have shown. We're certainly looking for like-minded people, and maybe for people who would like their data space to have better semantic metadata. And then we can provide services or just help out with advice depending on what the case may be. Next is
The next one is not a question. I think it was like some information on what is being done by the European Commission and the CIMIC. What I propose from the Digital Factory Alliance is that they can send us more information, and I will share it with you too, on what they are working on with semantic specification for the data plane side of the connector, specifically in the linked data event stream specification. So as soon as we receive the advanced and detailed information, we will share it with you too, because I understand this can be very valuable both for UNDERPIN and smart tenants.
which metadata standards will be truly adopted by the dataspace community is a very good question and not easy to answer, because there's many data spaces that step upon AAS, Asset Administration Shell, in particular Catena X, and then Manufacturing X, Semiconductor X. Now I hear talk about Aerospace X. And we had a presentation at the IoT workshop discussing how how do you provide a schema for AES? How do you describe the schema of an AES dataset? And so that's done with AES submodels. And now I guess the most modern ways with the SAM, semantic aspect modeling something. This is the so-called ESMF, Eclipse Semantic Modeling Framework, right? But the connection between a SAM model and something done with OWL and RDFS is not clear. There's no canonic mapping how you can map that way of modeling data to an ontology or to a shackle shape. And this thing is becoming more important with initiatives like digital product passports and the ESPR. So I'm in chat with some guys from the CIRPAS2 project, and they have this problem on their hands. On one hand, people that want to use AES, then again, other people want to use other things like the United Nations Transparency Protocol. So I'm looking forward. There certainly is going to be a lot of collaboration in these domains.
There's totally agree. We're also working in CIRPAS 2 project actually, so it's great to know that we have more grounds for synergies. And hopefully there will still be time for the community to agree on common standards and common strategies to foster interoperability as well, and to actually drive the European data spaces community forward and position the European community towards the future too.
Right.
So I see there are no more questions. So given that we are already a little bit over the deadline, let's say, for the event, thank you so much for joining today at this deep dive. As you have seen, there has been a lot of participation and engagement in the questions. It has been very interesting. The event has been recorded, and the video will be available in the Digital Factory Alliance Digital Corner and also in the Vimeo channel. So anyhow, thank you so much, Petar Ivanov and Vladimir Alexiev, for your information. Great. Thank you for the presentation link too. And stay tuned for the next Smart Tenants Underpin deep dives that will be coming in the next 2 weeks.
Thank you.
Thank you so much. Have a great day.
Thank you very much. Bye bye.
Bye.
Bye bye.